Can you imagine training massive deep learning models without memory constraints? That is SMMF, our new memory efficient optimizer. Ladies and gentlemen, I'm Kwang Park, and I'm here to present this groundbreaking technology developed by our team, led by corresponding author, Professor Sig Lee. In this presentation, we will delve into the details of our newly proposed optimization technique, SMMF. We will start by introduction, then compare SMMF with existing methods. Next, we will present our experimental results to demonstrate SMMF's effectiveness. Finally, we will conclude by summarizing our key findings. The proliferation of edge devices such as smartphones, AI speakers, IoT devices has led to research in on-device AI inference. However, the need for centralized retraining to adapt to these driven shifts arises significant privacy concerns. To address this, on-device training is emerging as a promising solution. Training AI models is memory intensive, particularly during optimization. Optimizers like Atom consume significant amounts of RAM from 1 gigabyte to 100 gigabyte, making it challenging to train models on memory-constrained devices. This memory bottleneck is a major hurdle for on-device AI training. Atom-based optimizers suffer from a significant memory overhead to store both the first and second moment tensor. Existing memory-efficient optimizers such as Atom Factor, SM3, and KIM have made strides, but still fall short in addressing the memory overhead. We aim to develop a new memory-efficient optimizer, which can overcome the notable limitations detailed in the next slide. Existing memory-efficient optimizers like Atom Factor, SM3, and KIM have limitations. Atom Factor, while effective, introduces overhead by slicing the second momentum tensor using non-negative matrix factorization. SM3, designed for transformers, may not generalize well to other architectures such as CNN. KIM, an extension of Atom Factor, inherits its slicing-based overhead and requires additional memory for the confidence term. A common limitation among these optimizers is their inability to compress the first momentum, especially when it contains negative elements. Additionally, the sequential compression and decompression of gradients can hinder the optimization process by preventing the use of full gradient information. Our proposed method, SMMF, addresses the previous limitations. First, we introduce Square-Matricization, which reshapes the tensor into a square matrix, eliminating the need for slicing. Second, we factorize both the first and second momentums of atom, storing the signs of the first momentum's elements in a binary matrix for efficient compression. Finally, we reorder the compression and decompression steps to fully utilize the current gradient information, leading to improved optimization performance. Our proposed method, Square-Matricization, reshapes the given tensors into square matrix for memory-efficient optimization. It involves three steps. First, computing the total number of elements in the given tensor. Second, it determines the optimal dimensions for the square matrix by finding the factors of the total number of elements and minimizing the differences between them. Finally, it reshapes the tensor into square matrix with the dimensions found in the previous step. According to our theorem 3.1 and 3.2, our method reduces the space complexity from product of a multi-dimension to summation of two numbers, resulting in substantial memory savings. For instance, when applied to the embedding weight matrix of BERT, our method achieves a 69% memory reduction, demonstrating the effectiveness of our approach. With the Square-Matricization, our proposed optimizer, SMMF, offers a novel approach to compressing both the first and second momentum tensor. To effectively apply non-negative matrix factorization to the first momentum, we separate the values and signs of the first momentum tensor. Next, we apply the factorization method to both the first and second matrices. Finally, we convert the signs matrix of the first momentum into a binary matrix. SMMF offers a novel approach to the compression and decompression sequence, leading to improved optimization performance. Unlike existing methods such as eta factor, SM3, and K, which compress the gradient before applying it to the weight, SMMF decompresses the first momentum, allowing for the utilization of the full rank of the current gradient. By postponing compression until after the update step, SMMF prevents the loss of gradient information and ensures that the model benefits from the most up-to-date information during the optimization process. Theorem 4.1 provides a theoretical guarantee for the convergence of SMMF in a convex setting. Under conditions A and B, as shown in the slide, we establish a regret bound for SMMF, indicating that it converges to a near optimal solution. We evaluated 5 optimizers: Atom, Eta Factor, SM3, K, and our proposed SMMF on various CNN models for image classification and object detection tasks using the ImageNet and Kako datasets. SMMF consistently achieved comparable or even better performance than the baseline methods. This indicates that SMMF not only reduces memory consumption, but also maintains or improves the model's accuracy. The most significant advantage of SMMF lies in its minimal memory consumption. While error factor and KAME introduced substantial memory overhead due to tensor slicing, SMMF effectively addressed this issue through its Square-Matricization. As a result, SMMF requires significantly less memory compared to other optimizers, making it particularly suitable for training deep learning models on memory-constrained devices. Similar to the results from previous image tasks, our experiments on transformer models, particularly on the WMD32K translation task, show comparable performance and memory usage. SMMF achieves similar perplexity scores to other optimizers, but uses up to 40 times less memory compared to previous memory-efficient optimizers. In pre-training tasks, SMMF also achieved comparable performance to state-of-the-art optimizers, significantly reducing memory consumption. However, in the case of BERT, all memory-efficient optimizers showed lower performance compared to them. We will delve into this observation and potential results in the next slide. So, why did BERT show lower performance with memory-efficient optimizers? This phenomenon can be attributed to the fact that BERT does not operate in a low-rank space as indicated in this reference. Nevertheless, numerous studies have demonstrated that the effectiveness of low-rank approximation techniques in language models is closely tied to the presence of low-rank structures in their weight matrices. This implies that low-rank memory-efficient optimizers such as Eta Factor, SM3, K, and our SMMF remain effective for our other models. This slide presents the final experimental results on fine-tuning various transformer models, such as GPT-2, T5, and Llama for NLP tasks. SMMF consistently achieved comparable or even higher performance compared to other state-of-the-art optimizers, while significantly reducing memory consumption. As shown in the table, SMMF required significantly less memory compared to other optimizers, such as Atom, Factor, SM3, and CAME. For instance, on the QNLI task, SMMF achieved an accuracy of 91.4% on the Llama 7 billion model, which is comparable to the performance of Atom, but with a memory footprint that is less than 3% of Atom's. Similar results were observed on other models and tasks. In conclusion, SMMF offers a significant improvement over existing optimizers in terms of both memory efficiency and performance. SMMF achieves up to a 96% reduction in memory consumption compared to Atom. This is made possible through Square-Matricization, factorization of both the first and second momentum tensors. Additionally, SMMF improves the performance of deep learning models through reordering compression and deconversion sequence. Our convergence theorem provides a theoretical foundation for these improvements. Empirically, SMMF has demonstrated up to a 4.2 percentage point improvement in image tasks and a 14.2 percentage point improvement in fine-tuning tasks compared to error factor.